So you can hear. All right. Thanks for the introduction, Vijay. It's great to be here and actually see a lot of my teachers from IIT here. So it's a special honor for me to be like presenting my work, which was done during my PhD at the University of Maryland, as Vijay mentioned. So now that I have started my postdoc, like the work is in progress, so I would mostly focus on the work that I did before. So this is regarding a 5-qubit trapped ion quantum processor, which can be programmed arbitrarily to run algorithms. I will try to go through sort of the architecture that we follow to implement these algorithms. This is a picture of the ion trap that we use to trap chains of ions. These are like electrodes that apply oscillating voltages in order to form an RF Paul trap for ions. And then there is optical axis in these transverse as well as the axial directions in order to manipulate the ions. So just to give a brief overview of what is happening around the world in different platforms that want to achieve a quantum processor, there are several systems that are in this race. Just to go over a few of them, there is the NV diamond centers. These are defect centers in diamond. And there are neutral atoms in optical dipole traps that can be used for simulating certain Bose or Fermi Hamiltonians, as well as to do quantum information processing using like Rydberg blockades and things like that. There are quantum dots inside semiconductors that are manipulated using electric fields, photonic circuits where information stored in the polarization of the photons, and the qubits or the photons interact via a beam splitter operation. But more importantly, recently, like two competing platforms have come up with a promise to give you a programmable device. And one is the trapped atomic ions, and then the other are superconducting transpond qubits. Here you see this is a chip from Santa Barbara, John Martin's group, which has 5 qubits. And they are coupled for these 2 qubit gates via nearest neighbor interaction. So what are the like overall requirements to have a quantum processor? You need to have a system of qubits that can be scaled to a bigger size. You need to have high fidelity operation. You need to initialize and manipulate the qubit with high fidelity. You need to have a universal set of quantum gates that any interesting problem can be decomposed into, and sufficiently long coherence time so that you don't decohere before your evolution happens. All right, so in our system, we have 5 trapped ytterbium ions. Here you can see images of them, almost point sources of light, so you can kind of see the point spread function of the optics here. Anyway, so we have this 5 ions in a linear chain, and we can manipulate each one of them by addressing them optically. So I will go into the details of that. All right. So only recently, these two have started being programmed. And the reason being is that there are these gate sets that can be used to compile bigger algorithms in both these devices. All right. So in the introduction, I wanted to introduce you to the partial level structure of ytterbium, just to tell you what are the basic tools that we have here. The first one being the hyperfine split ground state manifold, where the MF is equal to 0 state is chosen for storing the qubit. So that can be thought of as a spin-half system or just a qubit 0 and 1. Being in the MF is equal to 0 state is first order magnetic field insensitive, so it has sufficiently long coherence times without you trying too hard, but then you can do magnetic field shielding to make it even better. The fine structure is in the UV, and that is used for as a nearly cyclic transition for Doppler cooling, state preparation and detection of these qubits. So I'll go into that. Once in a while, like once out of every 200 scatters, it falls into this D3 half manifold, and you have to depump it from that back to the useful manifold. right? So the two lasers to keep in mind are 935 IR and 369 UV. All right. So for state preparation, we start with an optical pumping. So first we Doppler cool it, we trap the ions, it's low enough temperature, we then optically pump it using light that is resonant with certain levels such that it pumps it to this what we call the dark state or 0 with a high enough fidelity. And we can further control the motional state of the ion by doing sideband cooling. This is something I will not go into the details, but apart from just initializing the spin state with a very high fidelity, we can also initialize the motion of each ion.
Sorry, Shantanu, the optical pumping, is that 3 different beams or just one?
It's a beam with different frequencies on it.
Okay.
Yeah.
But it's multi-component.
It has multi-components on it.
Practically, that's done by separate lasers or by modulating?
It's just like one laser which is modulated. These splittings are not very big. This is 2.1 gigahertz, this is 12.6 gigahertz, so just using traditional electro-optic modulators, you can put like sidebands on it. State detection is important because, because the infidelity of your quantum gates should add up to your process fidelity. The state readout being very high, you can very well know what the process fidelity is. Anyway, so what the state detection looks like is there is a light that is resonant between the f is equal to 1 and f is equal to 0 manifold of the ground and excited state. And if I shine that light, there is a cyclic transition that happens between the 1 and the 0 manifold. So the atoms ends up like scattering a bunch of photons. If you look at the probability of how many photon clicks you get, if it's in a bright or 1 state, it gives you a Poisson distribution. Whereas if it's in the dark state, I don't get any photons. Now this distribution is not perfect. There has to be a discriminator, so there is a little bit of overlap between the two. And that gives me a little bit of infidelity in the discriminator method of doing a single shot readout of the spin state. And that fidelity is a little over 99%. All right.
So this is number of photons given unit time?
Given unit time, yeah.
You're actually looking for clicks, number of clicks.
Yeah. So if the click is more than 1, then it's a bright state in our case.
What's that time typically?
150 microseconds in our case, but it can go down to as low as 10 microseconds, maintaining the same fidelity. It depends on how much light you collect. So there are people who will collect like 10 times the more light than we do. All right. All right. So moving on. So these were the state preparation and detection were like our dissipative processes. We do this single shot readouts. Now I'm moving on to the coherent control of the qubits. And that is performed using this Raman transition. So I have my 2-level system. And my excited states are the p-half and p3-half levels. So there is this commercially available pulse laser, which is at 355 nanometers. And it has a magic detuning from these two that gives a very small stark shift while off-resonantly coupling to this excited state. So the idea here is to have a beat note. So these two laser beams have a frequency difference, to have a beat node which is resonant with the qubit splitting, and then you end up doing coherent Rabi flops between the two levels. But it's a pulse laser, so in the frequency domain, it looks like a frequency cone, right? So in order to get these beat nodes, we end up getting a bunch of beat nodes. So what we do is we shift one frequency cone with respect to the other in frequency, and that lines up, let's say, the 0th of one and the 107th of the other, and so on and so forth. So there are all these different frequency comb lines that all have the same beat node frequency. Here, omega hyperfine being the qubit splitting, and mu being the tunable detuning of that beat node. So by applying this Raman process using this frequency comb lines, we can do coherent interactions. And just to find out like what is the coherence, relative coherence between these beat nodes and the qubit itself, we do a Ramsey kind of an interferometric measurement. And if I extrapolate these things, then it is almost half a second. That's the coherence between the control and the qubit. All right.
This is a standard Ramsey.
Yeah. Yeah, so pi by 2, and you wait, and then a pi by 2. All right. So what kind of coherent transitions do we care about? All right. So I already mentioned that there's the spin half level. So it's a zero and there's a zero state and there's a one state. That's the hyperfine splitting. But then each ion has a motion because it's trapped in a harmonic potential. And you could think of these harmonic levels also giving you like splitting in the transition, right? So if I were to flip my qubit without changing n, or the average phonon number, then it's called a carrier transition. I just do Rabi flops. But then I can tune my beat node in a way so that I increase or decrease the phonon number. And those are my blue and the red sidebands. And these are motional red sidebands. So as the qubit flips, the motional quanta also changes by 1. So these are my first sort of red and blue sidebands. So if I have a single ion, I have one mode of motion, and I see one of these lines. If I have 5,
what's the vibrational frequency?
It's around 3 megahertz. If I have 5, then there are multiple modes. I'm showing just the 2 of them. One is a common mode, one is a rocking mode, or the tilt mode. But there are 5 of these, and it forms a forest of transitions around these red and the blue detunings, right? So because these are different kinds of motion. And these motions are like normal modes of motion. So the entire crystal of ions together oscillate. They interact with each other, so they're coupled oscillators, interact with each other through Coulomb interaction. So in the end, in long time scales, you end up getting these like normal modes of motion. So here I have 5. All right. Anyways.
I mean, I guess there should be a whole ladder of modes, right? Or are you only sensitive to 5?
There are 5, so in any given direction, so there are like 3 orthogonal directions. Yeah. So it'll be 5 along each direction. So there are 3 directions, so there will be like 15. Yeah.
Sorry, just clarify. So omega x here is at 3 megahertz.
Yeah, that's right.
And then the different normal modes are actually equal to 4 pi here.
Yes.
I'm surprised by the modes shapes you have drawn. So these are actually moving like that. I thought they are modes in the.
Yeah, so those are the axial modes, and those have lower frequencies. They're close to the carrier transition, so we don't couple to those modes. We select the transverse modes to do all our quantum operations. So I'll describe like the 2-qubit gates, and for that we use the transverse modes and not the axial mode. Yeah, but people use the axial mode. Yeah. All right. So let me state the outline of the talk. So in the first part, I will be talking about a few algorithms, the first one being the quantum Fourier transform, examples being the phase and the period estimation. And then I'll talk about recent results on fault-tolerant preparation and detection of logical qubit. So these are the papers. And then in the second half of the talk, I'm going to talk about a simulation of a Hubbard model. And here I'll be talking about local vibrational modes of the ions and how those modes can talk to each other. Right. Okay. So this is the bare bones of the processor. The schematics is that you have a chain of ions. You have Raman beams which are counter-propagating such that the delta K vector of these beams are lined up in the transverse direction. So that is how you will excite the transverse motional modes of the chain. All right. So one is a global beam that illuminates all the ions. The other one is an array of beams. Each one of these beams are individually switched using a multi-channel acousto-optic modulator. And then focused with a good enough resolution so that you could address each ion. Right? So here's my laser on the table. And that is the 32-channel acousto-optic modulator we are using. Like here, I'm just turning on 10 channels, and this is just taking an image of the different beams that are turning on. Anyway, so you can switch any pair of beams or any number of beams at will. So that is our main control for selectivity.
So what's happening is there's a single laser beam which is being split into several components that's going into this modulator.
Yeah.
And then each of that beam can be
Yeah.
modulated and focused wherever you want.
Yeah. So this AOM could be thought of 32 AOMs sitting right next to each other, miniature. For detection, the reverse happens. So here is an objective, microscope objective, that collects light from each ion with high enough Na so that you get a resolution of about a micron on each ion, and then focus the collect light onto individual channels of a multi-channel PMT. So these are like PMT counts versus different channels. So each ion is spaced by one channel. So here I can get clicks from each ion and do a parallel single shot readout of the state of 5 qubits. All right, and this is the vacuum chamber. The ion trap resides inside this main chamber, which has re-entrant windows, such that we can have small working distance of these lenses that need to focus light and collect light aggressively. Here is a picture of a bunch of ions that are loaded deterministically. So there are loading techniques, and you can like load however number of atoms you want in the chain. This is a picture of that. The trap from the side looks like 4 blades. So RF is on these 2 blades, and these 2 are DC. So it forms like a quadrupole potential, which is oscillating.